Can you hear me? And give you the the ability to know how to go out and get those other tools, right? So part of what our responsibility is through other courses, through Capstone, is to teach them how to to help them learn how to learn, right? How to go out and seek resources and information that isn't at their fingertips, right? Because they're not going to graduate knowing everything. So how do they go out and learn how to learn? How do they go out and get those additional resources? We want to familiarize and emphasize kind of that design methodology, design thinking process. And so we, utilize that process embedded within our Capstone to help them design a solution for their client. And then lastly is to really be able to communicate well with their client, with their fellow students and other stakeholders as a part of their project. Oops. So the way, and again, I will tell you, our Capstone program across the college, there's a lot of continuity, a lot of consistency in the way that we do things. I will tell you a slight maybe difference in the way that I do the civil environmental is that I really teach as a class. So it's not just project based. So it's not just them working on their Capstone projects, but I also embed a tremendous amount of other content within that class. So I actually meet with my Capstone civil environmental groups twice a week, on Mondays, Wednesdays for an hour each time. And in the fall semester, we focus very heavily on the project focus on that design methodology, that customer discovery, the conceptual design and development, design alternative, looking advantages, disadvantages. From the course perspective, it's all about professional development. It's all about engineering practice. And so you can see some of the concepts that I'm introducing to my students here. It's not just introduction to Capstone, but it's like giving them advice for as a new graduate. It's talking to them about contracts. It's talking to them about the business models, right? So when you go work for a company and they charge your time at $100 per hour, and you ask, well, why don't I get $100 per hour, right? Where's the rest of the money go? We talk about that, right? So it's to understand that, it's to understand how the office works, what they're going to be expected to do. We spent several weeks on engineering ethics. They'll actually take an ethics exam as a requirement of this course. So that's an NSPE ethics exam that I give them. And so we generally have very ethical students. They do very well in that exam, which is good to hear. We talk about, the engineering workplace and how that has shifted and transformed, right? From being just solely technical, but now you're being asked to not just do the engineering, but you're also asked to go meet with clients. You're also asked to incorporate and think through ethics and other things in your projects. Talk about civic duty and their responsibility as an engineer to their profession and to the community. So be able to serve, their organizations, to serve the profession, to serve others in ways beyond just their work that they're required to do. We talk about hiring principles. We talk about how to lose clients, how to hold on to clients, right? We talk about the benefit of repeat business, right? So if you're a company and you're constantly having to go after new clients and you're not having substantial repeat business, repeat clients, your company's going to go under. So we talk a little bit about that and kind of go through those aspects there. As I mentioned, we really follow kind of the design thinking methodology in our Capstone. So we start in the fall semester with once they get their projects and they met their clients, they understand what the problem is. The first thing we kind of do is this empathize. We this customer discovery process by which they understand who their stakeholders are, what the needs of those stakeholders are, and then from those needs and their stakeholders, they prioritize, and I'll show you a bit more here in just a second, but they're prioritizing those stakeholders, right? So not every stakeholder is created equal. And so it's understanding, who do you keep close to the chest? Who do you just keep informed? And so those are some of the things we talk about. And then we move into this project understanding phase where the students have to more fully understand their stakeholders, their needs, but then connecting those needs to values, to opportunities, to risk or competition, as well as what are the codes and jurisdictions or regulatory actions that are connected into what their design is. So it's really helping them to be able to connect the dots between the stakeholders and needs to how to develop their project, what information is needed, what understanding is needed to be able to develop their design ideas. And then we go into project concepts. And so most of my teams will develop 2 to 3 different design alternatives. Those design alternatives will have list of advantages and disadvantages with order of magnitude cost estimates associated with it, and then they'll also connect that with how they specifically either meet or don't meet what the original needs of the client were, right? So we can't be everything. I tell my students, you can't do everything to everybody, right? So your projects may not have every need satisfied. And so you just need to be able to be very clear in terms of how your project is meeting that. Moving on into the spring semester, what we do is we finalize one of those design alternatives, or we create a hybrid version of the design alternative. So sometimes clients are like, we like what you did with design alternative 1. I really like what you're doing with 3. Can we do this aspect here and that aspect there, combine it into a hybrid version? And by the second week of January, we finalize that, and then moving into what I call heavy engineering design. So this is where they're developing their engineering drawing sets, really the entire blueprint for how that project will unfold. So it's entire drawing set for our civils and environmentals. And then once we get done with that and we finalize that and go through a lot of different iterations, a lot of redlining, a lot of updates and so on, in the spring, we turn it over to the client and let them move forward. And we've actually had a lot of success stories in our civil environmental where clients have gone on. They just actually did a ribbon cutting for a large park down in Valdosta. We've done a couple of park designs in Spalding County, a roadway redesign in Hawkinsville. So we've done a lot of different things there. It all starts in the fall semester with the client meeting and a site visit. Tell students you can't do a project if you've never been there, right? So we're not going to be those that always do the design from the backs of a computer. So we get out there, get out there and walk the site, take lots of photos, take lots of measurements, understanding what challenges may exist, what opportunities may exist as a part of the project. This is from a few years ago. This is just to show you where we're at in the state. We're doing projects all over the state. In fact, this year we've got 2 projects in Florida, so those site visits, yes, long days. So we'll do that. But we go there, we meet with the client, take lots of photos. It's always really exciting to go see the project sites and see what we need to do there. Moving on, like I said, we go through this design thinking process here, and these are forms. These are just sample forms for which my students will complete. Our students in Capstone will complete. And as I said over here on the left, it's who are your internal stakeholders, who's the external stakeholders, asking questions about what is each of their needs and how are those needs need to be met. And then down here is prioritizing, right? So who do you keep close? Who do you keep satisfied? Who has lots of authority on your project? And then, who is it that has lots of interest in your project? And so just understanding that. Then we move into that, like I said, project understanding with connecting the stakeholders to the needs. So this stakeholder has this need, this stakeholder has that need. And then again, looking at, human value and opportunities, financial opportunities and values, competition risk. An example I gave yesterday, I was talking about project understanding, and we're talking about a park as an example. And it's like, a competition would be like, I designed a park and there's the exact same park in the county right next door, right? Like, why would they want to come to my park when they can just go to that park? So what makes your park unique? What's going to differentiate your park from their park, right? A risk could be that, hey, you know what? I've designed this park to be 2 acres. And we've now outgrown it, but that park's now landlocked. I have no additional land to be able to develop for additional amenities to that park. So you've got to be thinking through not just what is now, but what is the risk in the future. And then again, a big part for us is making sure that our students understand code requirements. So how are they applying, codes, Georgia Stormwater Manual, the Erosion Sediment Control Manual, GDOT standards, building codes, et cetera, to their designs. And then we'll go through, and what we generally do is have them develop one of these sheets, concept worksheets for each of their design alternatives. And so that makes them very intentional about their design, what their idea is, how it meets the specific needs of the stakeholders, and then, what are the advantages, disadvantages of that. And then they take that, and that's a textual type of design alternative, and then they put it into drawing, and they actually draw what they're saying they're going to do there. For the fall course, these are all the different assignments. So beyond just the design part, right, they're working on, beyond just the project part that they're doing an ethics assignment. They have a professional licensure assignment. They're meeting with a faculty or a PE that's not associated with their project to get a different perspective, right? They're meeting with the Career Center. I asked them, I say, you've gone 4 years, right? You probably want to get a job. Let's figure out how to do that. Professional meeting attendance. They have to go to a non-UGA meeting. So they generally have to go to like an ASHRAE professional meeting or an ASE professional meeting or some meeting to go network and get connected, right? See the benefit there. Become a member of 2 professional organizations. Get a professional periodical subscription. The leadership we'll talk about in a minute. They do a 360 peer evaluation, design notebooks, milestones, ethics midterm exam that they have to take. And then they do a presentation, and then obviously the design report and client presentation. For the spring, project focus is all about taking your design to complete. So we're working to develop their drawing sets, making sure those drawings and their designs meet acceptable or applicable codes and ordinances. And then for the course part, a little bit less rigorous in the spring. We really do FE reviews. So I go through all these different FE reviews. I give lectures on these, and we have them do homework assignments as a part of that. Our success rate, for example, in civil last year, our pass rate for civil engineering was on average 77%. The national pass rate is 63% for that exam. So we're about 14% on it. I know, it's awesome. So here's an example of what we're doing in kind of over the course. This is what we get. So the city set, this is down in Candler County and Metter. They're like, hey, we want a road from here to here. I don't know how to do it, but that's what we want. So I'm going to draw a straight line. That's what we want, right? And so our students go through and they evaluate this property, and there's a bridge here you can't see down here. So GDOT code requires you to be 1,000 feet away from an overpass. So that prevents where you can tie in. We've only got a certain amount. This little green space right here is a wetland. Traditionally, you don't want to go through wetlands. So the landowner was like very okay with that because he was going to go work with the Corps to get wetland credits because he's got electoral land. So he's going to do a swap. So it actually worked out fine. So our students would go through conceptual design. This is the design alternative that the client chose. And this is actually a partnership with the landowner and the city and county, and actually the school district, because it was initiated because school buses had to go from a multi-million-dollar new school here down this road all the way downtown, cut across, and come all the way back. They needed a thoroughfare. So basically, we worked with multiple people, came up with this design alternative as a concept, and then this is one of the sheets. Again, the sheet drawing set's probably about 20 or 30 sheets, but this is just the site design for that. And they subdivided it. In this project here, we actually worked with Terry School of Business to understand, because the site developer at the landowner's 32-acre cotton field. He's like, well, I want to make this commercial. I want to bring businesses in. And so we're like, well, what size businesses? So we went to Terry and said, hey, look, for Metter, what businesses would come into Metter, right? So not just any business going to come in there. So based on what is in the surrounding area, they gave us a couple of ideas for companies or businesses. And so we made appropriate sized acreage lots to fit just specifically those buildings. I'm about over 7 minutes. All right. So we put our students in front of the stakeholders. This was a commissioner's meeting down in Spalding County. So you can see here's our students. They're going to present their product, our 3 students here, and then a board table, very professional. They have to get in there and give a really nice presentation. That project was very well received. They're actually building that right now. Spring course requirements. Again, we do a peer evaluation, FE review assignments, and then mostly just project related stuff. You'll see that we've done leadership, or I've included leadership here. This is something that is very unique to UGA. So we have actually, if you're not aware, have what we call the Emerging Engineers Leadership Development Program. It's in partnership with the J.W. Fanning Institute for Leadership Development. And we piloted this program in civil environmental back in 2016. Myself and Dr. Jason Christian at the time, we did a review. There's a lot of other engineering leadership programs across the country. They're all selective. They're like 20 seats. And guess who those 20 people are? They're always going to be the presidents and the vice presidents of your organizations, the top people. We feel like everyone has leadership potential here, right? Everyone should have this. This is so important. And so we piloted it, launched it, and then went for the entire college in 2017. Last year, we had 450 students participate in this leadership program. They all will receive leadership modules over the course of the year in creating leadership vision, understanding leadership style, managing conflict, making group decisions, personal accountability, working cross generations, communication, stakeholder, and so on. And what we do is we map it. It's threaded into the Capstone Design course to where it's connected, and students are doing these leadership modules at timely points throughout the year that connects with what they're doing. So for example, Exploring leadership style, we actually do that very first thing. We utilize their leadership style in the selection and makeup of the project teams. Then we move in talking about communicating, right? So they may have to communicate or they're going to have to communicate with their clients, many cases through Zoom or other things for initial meetings. How do you communicate with your clients? We talk Fanning Institute. The Fanning, we pay them to do that. So we do stakeholder mapping and engagement. And then about this time, they need to start making decisions as a group. And then at some point, someone's not doing something in their group and there's conflict. So how do we manage conflict, right? And then we we go into the spring semester. You know, their clients may be of different generations, right? They may be baby boomers, Gen X's, right? How do we understand what different preferences are across different generations? We talk about risk and entrepreneurship. Creating your vision. What is your plan now and beyond for creating a leadership plan, and then developing your person accountability? So we do that. We do assessment pre and post. So you'll see, the before is the black. So you see here, strongly agrees pretty small. Post, the red, very high, right? So the students are learning and they're developing the skill sets and building confidence in their leadership abilities. You know, what we always do is we emphasize that leadership isn't necessarily positional leadership. I think a lot of students think of it as positional, right? Supervisor, CEO, president. It's more personal leadership, right? So what is it that you're doing within your group, within your team, within your community, within your company, organization, or even just here in the college? So with that, I want to stop. I probably went a little bit longer than I was wanting to, but I wanted to open up for some questions and answers. So what questions? Mike?
So you're teaching a lot of different concepts. So now I know that I teach a little bit of ethics in 1920, but let's say just like codes and regulations, in their 4 years, have they already been introduced to all these things, or there's sometimes it's only to Capstone that they finally realize all the codes and regulations?
Well, for ethics, I'm hopeful that they're getting ethics every single year in our curriculum. I hope that those are things that are being talked about, right? I will tell you within the civil, because I know that very clearly, is that we taught codes from day one, right? So if you're doing surveying, then you understand surveying licensure, you understand boundaries and codes. You know, we get into like reinforced concrete design or steel design or natural resources, like there are Georgia stormwater codes, there are reinforced concrete codes. I mean, they are. So they're getting it. I mean, it's all they do. I mean, I think they do. But the key here is it's all about building confidence, right? So we want them, I always tell them, Capstone's your audition, right? So you're doing Capstone. If it doesn't work out the way you felt it or wanted it to, it's okay, right? But it's your test before you go out into the real world, right? You go work for a company. That's the real stuff. So, James.
Yeah, I have a lot of questions.
Oh, God. You can ask our remaining. We're good.
So on your fall assignments, like you show, there's a whole list of things that you have to do. But I noticed that some of them may have a financial component. So joining 2 professional societies.
Nope. I give them a list. I've got a whole page list of professional organizations that are all free. I don't ask, the students will not pay for anything. If I'm asking them to do it. Correct. Nope. If we go to, I've got connections with like ASC, for example. Most of our students have or go and attend like the ASC Northeast Georgia branch meeting. And so what I do is I work with, I'm an officer, so maybe I'm biased there, but we work with them so that they can get connected to go to that meeting and attend that meeting. So we had a meeting just about every month, basically. And so they can join that and attend that and connect with people as a part of that. It's no guarantee. Now they can't, if I tell them like professional organization, you want to join and become a member and it's not on this list and it's not free. Like I'm not requiring you to go. If you want to go join this other one that does charge $30 or whatever, and it's really of interest, like that's on you. You can do that. But there's plenty of opportunities that are completely free to students. Yeah. Are we good?
Yeah.
You haven't. We'll come back, Dominic. Well, yeah.
If there is a financial, if there were a financial component, how would that affect accessibility from
Yeah, I would definitely work through that. I mean, for me, I want to make sure that everything's accessible. I want to make sure that nothing that I'm doing is a financial burden, right? So it's like, for example, we go on these site visits. One year I drove 3,000 miles for site visits because I don't want students to have to do that. Even though they can get reimbursed, like I don't want to put that burden on a student or a group to have to travel. So I mean, I've already been to Hartwell twice this year. We're going to Spalding County on Friday with 2 groups. I'm going down to Jacksonville, Florida in a couple of weeks. Like I'll do all that. I'll drive all that. So I don't want my goal is to make sure that there's not a financial burden on that, on any of those particular things for students, for sure.
So if there's a capstone project in Costa Rica or
I've sent 2 students to Haiti before.
Oh, really?
I have, for free. I mean, they didn't pay for it. So we found money for it. Yep.
So that's awesome. I have a bunch of questions. I set for 3. You took one of those 3, so I'm down to 2 now.
Whew, man, look at that.
Yeah, no, it's really interesting. So I was wondering, when you talk about the different steps in the process, at the beginning you talked about how they interact with clients, finding out what the kind of like goals for this project. And I was wondering how you talk with them about the differences between clients, user groups, stakeholder that might not be clients. So how do you like guide this discussion, and what do you see among the students? How do they understand that?
So we recognized that need years ago, right? Because, when you go to meet, it's not, when you're doing a project, and though it may be the county of, city of, you're not just doing that project for that county administrator, right? You're doing the project for the citizens. You're doing the project for the school board. You're doing the project for the, medical centers that are, it could be a lot of different stakeholders, many that you're not even thinking about like right now. And so we thought about that. And that's why we've embedded in our leadership program, we have stakeholder mapping and engagement. So that leadership module is specific to you, exploring who your internal and external stakeholders are going to be, what their roles and what their involvement is in your particular project. So in some cases, it may require you to have a deeper connection. You're going to go and interview these people. You're going to be talking to these people, right? You're going to be having these really lengthy conversations. While others, it might be, well, we just need to make sure we're considering that, right? So it's not like I'm going to set up a table on the corner of whatever street and talk to every single citizen that walks by. I still need to make sure I'm considering them, right? But, I always give the example of the park project, right? That has lots of stakeholders. That's got tourists, right? So Chamber of Commerce, we want to talk to the Chamber of Commerce about how this park project will be used to increase business and development and tourism and whatever else, so on, right? It's also the police station, right? They want a park that is safe and accessible and visible. They want, it's the neighborhood next door. They want a park that's easy and accessible, but it's also quiet and have a lot of light noise, right? So there's a lot of different, different things that have to be considered. Those are the discussions that are being introduced on how to do that, how to explore that through our leadership module. And then we have those types of conversations too, like individually. I meet with the group and say, well, who's your stakeholders? And then I'll say, well, have you thought about, have you missed this? Those types. Did I answer your question, Down?
Totally, it's really fascinating. There is so much overlap with the training and the class I'm teaching. So I'm preparing the students for stakeholder interviews just this week. So that's really fantastic. And maybe final question.
I'll send.
We are out of time for questions.
I'll tell you what I'll do though. I'll share the video for stakeholder mapping with you. I mean, I've got a video for that. So we do videos and we also have in-person modules. But for that one, I've got a video for it. I'll share it with you.
All right.
Happy to talk.
Thank you. And next up, we have Dr. David Stooksbury. So it does clip. It does clip.
Hey, well, thank you, Stephen. I know we put forward the proposal for 2-semester sequence for our non-thesis graduate degree, and we're calling it Advanced Engineering Design and Management. And it's basically what Stephen's course is, but on steroids. So for the graduate students, you can have a sense of what they're going to be. Stephen also mentioned METR. About 15 years ago, I realized how Georgia was changing when Casey Doss and I stopped to eat dinner in Metter. So we had a native Georgian and a guy from India. And we finally found a Mexican food place where it was actually very useful for the fact that I could speak a little bit of Spanish. It was that type of Mexican. So we had a Georgian, an Indian, and a Mexican food place where Spanish was useful. They had karaoke, but the guys that were doing karaoke were good old South Georgia white farm boys doing karaoke rap. And you talk about the cultural fusion that was going on in that little Mexican restaurant in Metter, Georgia. I said, Georgia is changing. And it was kind of exciting to see that. So that was kind of exciting. Stephen mentioned that engineering is changing. And, one of the things that we all are aware of is that, 40 years ago, we really put an emphasis on that hand calculations. I was the last generation or the last year that they taught slide rules. Yeah. What's the slide rule? Slide rule. Slide rule. And so I actually used to know how to use one of them. They're really cool devices. But what we're doing is changing. The computations now is going to be in the real world is going to be through an app or a software package. They're not going to be doing the hand calculations that engineers used to do. And so one thing I've done with thermodynamics, and which is probably one of the more conceptually dense courses that students take, I can show them most engineering devices. It's difficult for me to show them energy. Here's a picture of energy. That just doesn't happen. So it's very conceptually dense. And one thing I was noticing that I used to have with students, I think we all do this, is say, well, write down your assumptions when you're working a problem. And they could give me the right assumptions. And they might say, oh, it's insulated. This is adiabatic. The next thing I see is they have thermal energy transfer as part of their going, okay, they gave me the right assumption. They didn't understand what the assumption was. They memorized an assumption. There was no conceptual idea about that. So what I've done is I've really cut down on credit for the right answer. They also know that I am always emphasizing we want a reasonable answer. Don't ever think it's the exact answer. We want a reasonable answer. And so they get most of the credits actually for setting up the problem. On a 30-something point problem, they might get 6 points for the correct answer. And the value of this was shown to me during COVID when we were doing stuff online. I had students who could not tell me exactly how they get the problem or even what equations they used, but magically they had the right answer. I don't know if that was related to the fact that during exams, I would see my questions popping up on Chegg during the exam. Yeah, so this kind of solved that problem, even though I was doing this before we went online. So, but that turned out to be a nice benefit, was made cheating much more difficult. The other thing is students have come and told me, I really didn't like this when we did it in class until I realized actually I was really learning this stuff. And then when I took the next course or other courses that depended on this, I said, I really do know this because I'm making them think through. We know anybody who's taught thermal can immediately tell me, oh, for a turbine, the output is going to be the change in the enthalpy of the fluid. Okay, but do you have any understanding of the reason that it's the change in enthalpy? So that's what I'm emphasizing here. So I'm going to work through an example. This is actually, I work through all the examples in class this way, or the ones that should be done this way. And then I also give them a detailed handout for those who just need some more hard copies. of it worked out for them. So this is one of the handouts I give where I work it out in detail. Okay, so the problem is we have cold water leading to a shower enters a well-insulated, thin-walled, double-pipe counterflow heat exchanger at 10 degrees C at a rate of 0.95 kilograms per second, and is heated to 70 degrees by hot water that enters at 85 degrees C at a rate of 1.6 kilograms per second. Then determine the rate of thermal energy transfer. I really emphasize, I don't ever call it heat. Heating is a process. It's thermal energy it's energy that's being transferred. Heat's not being transferred. It's energy that's being transferred. So I will, but since the next course they actually take, it's called heat transfer, I will like to say that. Then determine the outlet temperature of the hot water and the rate of entropy generated in the heat exchanger. Okay, so the first thing I do, and since it was a handout, I actually give a little discussion here. That's not germane to what we're doing. The first thing I do is I ask for 2 points. State the type of system and the flow associated with the problem. Okay, so type of system, is it open or closed? And then the flow, is it no flow, steady flow, or unsteady flow? Now, if it's closed, it's no flow. I have students who tell me it's closed and immediately give me flow. Okay, that's an indication to me you're missing an important idea here. So this one is going to be an open system and steady flow. I hope everybody got that. Since you're all engineers. Okay, so hey, you got 4 points, and you haven't done a thing yet for the problem.
How many points did you pass the exam?
About 100. Okay. Okay, now for 6 points. Okay, for 6 points, name the physical laws and give the associated canonical equations needed to solve this problem. Canonical equations is what I'm calling, canonical means the fundamentals. So what is the fundamental equation, the whole thing. So in atmospheric sciences, when we do Navier-Stokes, our Navier-Stokes in atmospheric sciences is actually larger than engineers because we actually have Coriolis terms in there. So we have cross products in there. We also do it in 3 dimensions. Atmosphere refuses to work in 1 dimension, so we actually have to do it in 3 dimensions. So what physical laws might be useful for this one? Oh, the conservation of mass. Okay, now the fact that they told me it was an open system, and I always keep referring back, you told me it was an open system, that tells you have mass. So you have to tell me it's the conservation of mass. And then here is the canonical equation associated with steady flow conservation of mass. Okay, so they got credit there for that. Okay, then the conservation of energy, yes. The fact that we are putting in and out is an energy, is a mass balance, so it works the same way. And this makes sense mathematically in thermo because actually, since it's steady flow, the change in mass within the control volume is going to be 0. So the mass rate in is going to be mass rate out eventually. But right here, they're not setting anything. They're giving me the fundamental equations. Also, I do not allow them to have a formula sheet. If you're in thermodynamics, or you should know these equations. These are just kind of fundamental equations you should know. And when I'm teaching these equations, I'm always emphasizing, like, let's take that bottom equation, conservation of energy. I emphasize from very early in the semester, for an open system, there's only 3 ways to get energy in and out of the system. Through a heating process, a working process, or a mass transfer process. So if you know that, you can say, oh, I have thermal energy coming in through a heating process minus the thermal energy going out through a heating process. I have the work energy coming in, I have the energy going out through a working process, the next term. The next one is the energy associated with the mass flow in and the mass flow out. So if they really understand the concepts that we have energy coming in and the energy coming out, well, the equation looks long once you break it down and say, okay, there's 3 ways to get energy in and out: thermal energy transfer, work energy transfer, or mass transfer. And then we said, well, then that's going to be equal to the change of energy within the system. And that includes the internal energy, the kinetic energy, and the potential energy of the system. Now, since our systems are usually not moving, I emphasize to my students that if you have a boiler that is moving, thermodynamics is the least of your concern at that time. You need to get out of the building. Not respect to your reference frame, which would be the train. Okay, so, and you know, at first, the first time they see this equation, they kind of turn different shades of green, but then when they realize that if they're thinking about it, they realize, oh, that really is not that difficult to do. The biggest problem they have is, and this is probably more those who are not coming to class, that we have little KEs, little PEs, and big KEs and little PEs, and they have a tendency to get confused. That the ones on the left side are the kinetic energy of the fluids, the potential energies of the fluids, while the ones on it's the system. And so trying to, once again, emphasize that. So this helps me actually understand it. And in this case, we actually need to know entropy. So the entropy balance, or I'll allow them to call it either entropy balance, so you can't see it.
Points if they get big number 1 right. They get points if they get big number 2 right. Does it have to be consistent? Is there any points for them being consistent?
No. No, no. This is a big enough pain to grade as it is. I maybe will sometimes mention that. It says, but you know, they've already started losing points. Usually if they're not consistent, they're not going to get. So yeah, so I do have students who tell me it's no flow, and immediately they give me a mass equation. Okay. Okay, then the second law of thermodynamics, or entropy balance. So they got 6 points on this part. So they have 10 points and they haven't done anything. Okay, the big points is the construction of the assumption consequence table. Okay, here they have to go through the equations they wrote down and tell me term for term, what is the assumption you're making for that? And what is the consequence of that assumption? And that's where I was having problems. Students could give me the right assumptions, but they had no idea what the right consequence is. So the first equation was our mass equation, steady flow for both fluids. I got 2 fluids in a heat exchanger. So I have steady flow. So they're telling me the change in mass with respect to time of the hot, it's going to be equal to the mass rate in minus the mass rate out. And that's going to be 0 for steady flow. So they're going, and note that they will say that. Okay, so we've handled the first set of equations. Then we go down to the next one. Oh, heat exchanger is well insulated. Yep, I think that was actually important for heat exchanger as a whole. The rate of thermal energy being transferred in is 0. And so we're going, and I'm saying we're going to set those to 0 because in reality, they are not 0. I make a distinction between things that we're going to set to 0. We're admitting they really are not 0. We are setting them to 0 because no insulator is perfect. Okay, now in this problem I did, since this was a handout, I did talk a little bit about some issues with our system being the heat exchanger as a whole versus what the problem is asking for is the thermal energy exchange between the 2 fluids. So they did have to take that into account. And then we just go, here is for the entropy formula. I make a statement here, since once again, this is a handout, the entropy canonical equation can be handled below. I'm doing it in both locations because I really encourage them so they don't miss terms. They do one equation at a time, so just do the entire equation. But since they've already said that thermal energy flow is 0, they can do that. Okay, then. And so they just go through it. I'm not going to go through it completely, but measurable work interactions with heat exchangers. So we're going to set work in equal 0, the rate of work out equals 0. So they're going through each term and they're telling me what assumption they are making and what's the consequence of that. Okay, so this one, we see we keep going, we keep going, we keep going, we keep going. You know, we say it's steady state down here. And it's a real system, so we're going to have entropy generated. Okay, so that part, so they would have gotten 20 points to this point. So, oh, we'll see. So I guess we're up to 30 points now. No, well, 20 points for just assumption and consequences. Assumptions and consequences got 20 points. So we're up to 30 points now. Okay. For 6 points, give the working equations. The working equations are going to be, you took the big canonical equations, you determined what you were going to drop or set equal to 0. Now you're down to this equation. So give me that equation, because that I call it the working equation, because that's actually the equation you're going to use to solve the problem. So you get 2 points for each one of those. So here's your conservation of mass, conservation of energy, and somewhere down here, the entropy balance ones. Okay. So I said this is a handout, so I'm going through much more detail for them than would be necessary really to solve the problem. Okay. And I also emphasize that there are multiple working equations, just kind of depending on how far you simplified it. I will take the very basic one as legitimate, but students quite often know, though, I need to simplify that more, and I will let them do that. But so for conservation of mass, you know, we said, well, mass rate of hot water in is equal to the mass rate of the hot water out. So we'll just call that the mass rate of the hot water, mass rate of cold water in, and so forth. So that one's pretty straightforward. Conservation of energy, they had to do a little bit more work. I would have taken this one right here as okay, but then you can collect terms and you can, so you got many ones that you could do. And then the final one is the entropy balance. So, okay, so they got 6 points there. So we're up to 36. And then solve the problem. Okay, and I'm not going to solve the problem. 6 points there. So 42. So you see that. So they only got 6 points for quote giving the right answer out of 42. This is the work. And a lot of them don't ever give me the answer. Yeah. Yeah. I mean, yeah. They want to know, oh, did I really get the right answer? I like that. I like that idea. Numbers are safe spaces for engineers. Yeah, now they know they got the right answer. Even though, once again, I remind them, you have a reasonable answer. That is not the exact answer. So I do take off points for if you give me more than 3 significant digits. I take off points if you don't give me the right units. Yeah. Yeah. Yeah, and sometimes they get, and then when they looked up the values in the tables, because of course You know, I tell them, look, when I hand out the tables, I said, here's the answers to the exam. Somewhere in this 50 pages of table is the right number. So yeah, other questions on that?
So at this point, like they're talking about a heat exchanger, but do they actually get to see a picture of a heat exchanger to know what a real one actually looks like?
They have some in their books.
Yeah. All of a sudden it's like, well, what is a heat exchanger? What does that actually look like? And then it becomes more abstract to think about.
Yeah. And, you know, I think the person we had from Campbell University, I talked to her after her talk a couple of weeks ago, and they've actually gone out and bought some stuff so that the students can actually. Right. Yeah. When I'm teaching, obviously, since this is going to be how they're going to be evaluated, when I'm teaching them how to solve these problems, we do it this way in class. So you know, now I don't take attendance, but I take attendance on exam days because I can tell, because all of a sudden I will have a student that when they get to the assumptions and consequence table, they just kind of write down gibberish because they have not been in class, while those who have been in class are falling through. So I said, students are telling me this really helps them really learn it instead of just memorizing that, okay, output from a turbine is changing enthalpy. They'll come up with the same equation, but they now know where it came from. And if I change anything, it says, okay, you know, your turbine actually did have thermal energy loss. Your insulation was not quite 100%. So I can throw that into the equation and they can now work the equation because they're not memorizing a formula for a particular device.
Do you observe them? Do they actually go through in order? Because I've noticed that some of my classes, they write, like if I have 20 minutes for a problem, they'll write for 15 before they start thinking. This is like forcing them to think about it before they.
That's forcing them to think about it, and they do go through. And well, I said, you know, you thought it was this, and as you're going through, yeah, you can obviously go back and correct what you've already written. Quite often they'll realize, oh, I need the ideal gas law. Now that's an assumption. That's not a canonical equation because it's a reasonable estimate. So we don't put it under the laws. The laws we put, those are real physical laws. Ideal gas law is not. So they put that on this. So, they may realize later, oh, I need the ideal gas law. Oh, let me go put that in. And it says assumption. Air is an ideal gas. Consequence, the ideal gas law holds.
So you don't think they're doing step 5 first, but solve the problem first and then go from there?
No. Well, I got those who, yeah. The other thing I ask them to do is to please do it in order. Don't play Where's Waldo with me. And if it's Where's Waldo and I can't find it, because I'm thinking, okay, you're doing mass, now you're doing conservation energy, so you're going to do thermal energy transfer first, then you're going to do work energy transfer, then you're going to do mass transfer. Don't do it in order so that I can follow.
And this is on the exam. It looks the same, but it just has the Roman numeral, right? Just the statements of give this.
Yeah, so the stuff like the page for, this is what it will say. Construct the assumption consequence. I don't even give them the next line. I don't even do that. I don't give them that much. I just say it's constructed. Yes. Not really. Yeah, I typically ask 3 problems on the exam. And once again, this is basically a guided way of forcing them to think that if they're so muddled, if they're not, I found out before I was forcing them to do it this way, they were just so muddled that they were kind of searching, for the answer to start with anyways. So.
To what extent do they have practice constructing a table?
Every problem we do in class is done this way. I encourage, now what I encourage them to do for homework, to practice a few this way. But what I encourage, because obviously writing this down takes time. So what I encourage to do on their homework is to answer the first question: what type of system is what type of flow? Because then that tells you what laws you need and what form of the equations you need. And then write down the equations and then mentally go through the equations and say, what am I assuming? What's the consequence? So that they're not writing this all down when they're doing homework problems. Even though I encourage, so that's why I give out this handout. We do all the problems in class this way. So, they've seen multiple examples of that. So that doesn't normally seem to be the issue. In the back.
Because you're on the same page. However, for me, I'm dyslexic, like I could not follow any of those equations. So what I do, that's limitation, right? So what I do actually is I write out the equation and I'm saying, what's the first instruction? Steady flow, ddt goes to 0, and I show on the actual equation crossing out what I have left. For me as a person that cannot, if I see that written,
yeah, that's why I encourage them to do it on homework that way. But this is also, I'm testing concepts. So I'm really, let's say, I think thermo, to a lesser extent, fluids is conceptually one of the more conceptual courses we teach, along with statistics. So I don't know how I'm turning up teaching the deep conceptual courses, probably because I'm not an engineer.
How long is the exam?
50 to hour and 15.
Yeah, I wanted to know which one. What I mean is, like, if you have 3 questions in 50 minutes.
I have to, what I quite often will do is be very selective about which ones I do. This is the longest type one because this has entropy and all that. So one of them is going to be a closed system. So closed system is boom, 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 boom. So yes, I do have to be careful about that. Sometimes I will give them like chapter 6 and 7 in the thermo book. Chapter 6 is air conditioners, heat pumps. I'll give it, they don't do this with those type of problems. So not all the problems on the exam lend themselves to this. I mean, air conditioner, heat pump, efficiency problems and coefficient of performance, those are pretty straightforward. So